and thank you for hosting at this year's competition. We're representing the Surveying Engineering program from Michigan Technological University. My name is Jake Fabian. I'm a junior in the program.
My name is Matt Kunkel. I'm also a junior.
My name is Jay Trope. I am a senior in the program.
My name is Joe Anglem. I'm also a senior.
My name is Aaron Miter, and I'm also a senior.
Today, we'll be covering the project's initial concepts, the safety procedures we followed, the field procedures we did, and the results from what we did in the field. So to get started, when we began exploring ways that we could approach this year's theme of high precision vertical control applications, we all came to the conclusion that we really wanted to find a way to fold in our department's recently acquired laser scanner. And that led us to finding out about laser scanners being used for historical documentation on buildings that people wanted architecturally preserved or further monitored in the future. And that led us to our initial project concept, which was to construct a point cloud model from precise vertical control and then be able to utilize that not just for architectural preservation, but also future structural monitoring. It also allowed us to formulate the general methods we would use to accomplish that, which was to establish control points, perform a high-precision vertical control survey, and then use that survey to support the point cloud development. The structure we selected for the project is on the Michigan Tech campus. It's the academic office building. It was constructed in 1908 as part of a campus expansion project and was designed by a local architecture firm. It originally housed not just the school library and a mineral museum, but also the administrative offices. While the interior has been modernized somewhat over the years, the exterior still retains all of its original architectural details. For equipment and software, we had access to a Trimble R10 GNSS receiver, an S7 robotic station, and also a TSC3 data collector. For the leveling portion, we used a Leica LS15. We used a Ferrofocus 3D laser scanner. And on the software side, we used Autodesk Recap and AutoCAD Civil 3D. We used Ferris proprietary scene software, and for adjustments and calculations, we used Microsoft Excel. Our first concern was safety. An Industrial Advisory Board committee member provided us with the Wisconsin Department of Transportation's Survey Safety Manual. Although once it became clear to us that the entirety of the project would occur on the Michigan Tech campus, which is closed, the primary safety concerns with traffic were greatly minimized, and also since we had access to all of the buildings on campus, seeking shelter during inclement weather would be very easy as well. However, we made sure to collect emergency contact information from all the team members, as well as contact information for emergency medical services in the area. And since we'd be using mallets to set our control points, we made sure that everyone had an understanding of situational awareness. After addressing equipment and safety, we were able to move into step one, the establishing of our control network. We set 5 half-inch rebar links and a nail in pavement around the building, and then we took 2 20-minute GPS static observations on 2 of those points to begin moving into them. We sent that information to OPUS for processing, and unfortunately, we got an email back from them with the data accompanied by a warning about its accuracy.
So the next step in our project was to perform our traverse. And as Jake said, the GPS data that we collected, OPUS issued a warning. That warning was issued due to the fact that our points had to be extrapolated rather than interpolated because they lie outside of the Coords network that was being used for the corrections. So rather than do what we had initially planned, which would be to maintain our 2 GPS points horizontally for state plane coordinates, we would traverse through our points, our other 4 control points, and then rather than close on our 6th control point, which was our initial backsite, we would tie it as a new point, then occupy that point and close on our initial point so that we could adjust our traverse using the compass Bowditch method. Because our state plane coordinates had been contaminated from the OPUS data, we decided to also tie 2 concrete monuments in the field that had been set in a previous senior design project. We were aware of the monuments, but we later found that they had known coordinates so they could be used later by importing them into AutoCAD Civil 3D. We then imported our field points as well and shifted and rotated the traverse after it had been adjusted so that it would have the state plane coordinates. And that distance between our field measured points and the known coordinates differed by 1/100th of a foot, so we accepted that. And this is a map of the traverse and the surrounding area that we also completed for the project.
Following the traverse, we needed to measure the vertical positions of our control points. We did this using a Leica LS15 digital auto level, which is capable of measuring to very high precisions, such as 7/10,000ths of a foot. To ensure that we would reach this accuracy, we performed a peg test to reduce any instrument error and help calibrate the instrument. Once the peg test was completed, we began from the NGS benchmark that is on our campus outside of our school's library, as you can see in the image on the left. Throughout the level loop, we took various steps to reduce any error that would occur, such as balancing our foresight and backsight distances. We did this with the help of instrument readouts that gave us the measurement of our error that we had off. We also checked 2 different level levels on the instrument, and we used recently serviced equipment, and this would help us ensure that our setups were quality. We also used turtles that would help ensure that we had consistent turning point locations, and also would help us increase or would help us decrease rod settling. Finally, instrument software helped us reduce rod tilt, and would help. It would take multiple shots and average them to increase accuracy.
After completing the level loop, our next step was to set and locate targets around the building and then perform the scan. We set checkerboard targets, as you can see in the top right, or the top left, I mean. And we located their positions with the total station. And while we were locating the position, we had another team, another crew going out with the Faro scanner, which would then locate the targets, or they would scan the building at different angles. And in each scan, there would be 2 to 3 overlapping targets. This shows the location of each of the scans. The locations are arbitrary. They're not the same as our control points. And we strategically put them in places where we could see as many targets as possible, along with getting as much of the building as possible.
All right, and after gaining our scanner data, we would import this data into Scene, which is the Faro 3D scanner's software used to compile the point cloud data. After the scanning was complete, the point cloud was rendered and put into the state plane coordinate system, and we began this whole process by importing the scanner data into Scene, and we began a process called registration. There was an automated cloud-to-cloud based registration process that stitches all 8 scans together to create a point cloud of the academic office building. This makes the, excuse me. Next, we needed to georeference the point cloud to the state plane coordinate system. This was done using the known target locations of the checkerboard targets and comparing it to the points on the point cloud itself. Next, this was, after that was done, there was a regression analysis in the Scene software, which indicate the green circles as a light, and that is Scene's way of telling you that the scanner data is in fact positive. Next, we exported the point cloud into AutoCAD Civil 3D and Autodesk Recap, where we applied an elevation gradient to the recap file. And this right here is our final point cloud of the office building. This could be used as a future reference point to any future scans of the academic office building to test for any structural deformation or just to have it historically preserved. The results was a 300ths of a foot traverse misclosure for adjustments, 400 thousandths of a foot of vertical level loop misclosure, 500ths of a foot of level loop horizontal imbalance, a maximum control tangent area of 500ths of a foot, and the final product is a horizontally and vertically precise 3D point cloud. What we've learned is insight into project management, intercommunication among team members, tracking documentation, proper planning for field work, and technical and professional communication.
This time we'd like to thank our advisor, Yushinan. We'd also like to thank Bob Kilburn for loaning us the Leica digital level. We'd like to thank Don Lafreniere, who gave us access to the Geospatial Research Lab at Michigan Tech. That was absolutely crucial in processing our LiDAR data. And we'd also like to thank the Faro software engineering team who guided us through the georeferencing part of this project. And then we'll open this up for questions. Yes, sir.
So, were any of you versed on the scanning before you did this? I mean, did you guys go out and do some scanning prior to this project, or was this the first shot?
This was a learn as we go type thing. We all essentially had opposite schedules last semester when we performed this field work, so the crunch time involved just resulted in that doing kids.
Was your experience with the software, the cloud software and things like that, was it overwhelming? Was it
Very
people
overwhelming.
helped you with it, I'm sure?
It took us, honestly, the longest portion of this project was just trying to figure out how to tie our data together, bringing these multiple kinds of, the total station data and the point cloud data, just getting everything come together. And also space became an issue. On the computers at school, we only had 3 gigs of space, and we discovered that we needed far more space, and that's why we needed access to the Geospatial Research Center, where we could have a computer that was actually capable of storing the data.
Through
What about the roof? Did I noticed that it's not on the scan.
No,
What was the decision about the roof?
We were looking into the possibility of using a UAV to do an aerial LiDAR scan. We get heavy snowfall very early into the season, and by the time we finish with this portion of the project, it's already too late.
yes,
Is there a reason that you only use 2 to 3 overlapping targets? Wouldn't you get stronger results by having 5 or 6?
that was due to just the number of targets we had available. So we had, I think, 5 targets, and we had 5 targets set at a time, but we couldn't get all 5 targets in the scan at a time. And also, we didn't have the time available to take as many scans as we needed to do in order to have more than those 2 to 3 in each scan.
So how did you, when you started, then you only had 5, go around the building and tie back in? Because you would need to have tie into the same targets, correct?
Well, that's where the cloud-to-cloud referencing comes in. So it puts the point cloud together based on things like the walls and corners of the building. And then all the targets were really used for in the end was the actual georeferencing process. So the scan was together, and then we said, these are the actual locations of these targets, and it used that regression analysis to shift that and make it so there was in the state plan coordinates. Yes, sir.
Can you back up to your results slide? Right there. So what is control tangent error?
That's That is the level loop vertical misclosure and the level loop horizontal misclosure or imbalance. That's like those two together. It's like, it would be like the slope.
yeah.
We use Pix4D software that actually came with, or that comes with barcoded targets. Is that what you guys are talking about? When you only have a certain amount of targets, they actually automatically puts it in?
No, we had actual checkerboard targets, but we only had a certain number. I think we only had 5 targets in our lab.
Yeah, the project planning that you did, how you're going to set this up, as in most cases never goes exactly the way you planned it. What was the most frustrating part of the project that you had to revise and redirect your work?
Well, we were certainly not expecting to have the OPUS data come back with those warnings, and that really threw us for a loop for a while. So that ate into further time that we could have been spending in the field, just coming up with a solution to try and make that data the data we had already something usable in this project. So I'd say that was one of the primary areas that frustrated us, along with just tracking documentation in general from the beginning when we were starting to put this together.
I would say another large issue was the fact that the scene software that we had to install on our computers originally, it took a very long time to find out that we couldn't even use them on our computers due to certain delays with IT and among other things. But we ended up going to the geospatial research facility and using their labs rather than ours.
Yep, one more question.
This is more a piece of shared advice as opposed to a question. I too am along the coastline and know that if you take 20-minute sessions like you did, that you are going to be using the rapid static solution from OPUS, which requires that you're inside the reference points. If you had taken the 2 hours plus, the static version of OPUS is not dependent upon geometry, and you might have gotten what you desired. So just something for the future to remember.
That was part of the reason that we wound up using those previous senior design monuments, because they had done long sessions for those.
Thank you.
Thank you.